Well, hello everybody, this is Mr. Kinney. I'm going to go over about half of the review questions on the periodic table test review for 2014. Now, some of this stuff, I'm just going to tell you, like the first few there, you just go to those page numbers in your textbook. Okay, it's going to talk to you about those different theories. And really, Mr. Dalton's time, they kind of thought atoms were something like this, but there was four main rules that Mr. Dalton came up with. Probably the most important of which is that atoms of an element are identical. You can't change one atom into another. Atoms, when they form, they can combine together or break apart in chemical reactions, and they're always in whole number ratios. It's stuff like that. But you can see those four on that page. Mr. Thomson. Basically, Mr. Thomson was the one that discovered the electron because he had a device that was kind of like an early form of a TV set. He put a magnet near it, and the negative end of the magnet would repel these particles, which were electrons, and he realized, hey, electrons, if they're repelled by a negative end of a magnet, they must be negative. Mr. Rutherford. His experiment was... let me back off. So because of Mr. Thomson, Thomson theorized that the outer part of an atom had a negative charge. So that kind of changed what we thought for thousands of years. Then Mr. Rutherford came along. He's the guy that got a thin piece of gold and was shooting alpha particles through it. And most of the alpha particles went right through. Few of them got deflected. A few of them bounced straight back. So he's the one that came up with the idea that, hey, the nucleus must be mostly empty space. There must be a very dense positive nucleus center to it, because when these particles occasionally bounce back, the particles they were shooting were plus charged helium ions. So they had a 2+ charge. So these are fairly big. Had to have a fairly positive nucleus and very dense. So Mr. Rutherford figured out we had a nucleus. Mr. Bohr, page 128, he kind of came up with the idea that atoms tend to be in certain orbitals or energy levels, as he called it. He gave us what we now know as the Bohr model of an atom. Let me get this adjusted here. And I've just gone ahead and drawn the Bohr model. When you draw a Bohr model, you want to put the symbol in. You want to look on the periodic table. Carbon has an atomic number of 6. So 6 protons. It has the most common isotope of carbon that you see on the periodic table, has a mass of 12. So when you do 12 minus 6, you get 6 neutrons. Carbon is in period 2 of the periodic table. And whatever period you're in on the periodic table, there's carbon. That's how many shells you'll have. Every proton will attract an electron, so that means that there are a total of 6 electrons in carbon. The first 2 will go in the first shell, and the second shell will take the next 4 of them. So you end up with a total of 6 electrons in there. How many shells do the elements in the following periods have? Whatever period you're in, okay, here's period 1. These atoms have 1 shell. If you're in period 2, all those atoms, they have 2 shells. So it just goes by. I'm not going to fill these in. If you're in period 1, you have 1 shell. Or if you like, energy level, as they might be called, or orbitals. Okay, so, but anyway, whatever period you're in, you have 4 shells. Okay, you can fill in the rest. I'm not going to take time. List the charge, mass, location of the 3 subatomic particles. Oh, that's protons, electrons, and neutrons. Well, these guys have a mass of 1 for a neutron, and electrons basically almost 0. Okay, basically 0. Location. Protons are in the nucleus, as are neutrons. These are in the shell. And what do we got? The charge. I forgot the charge. Protons, positive. Electrons, negative. Neutrons, 0. zero charge, neutral, hence their name. How do you get each of these different particles? Well, for these two elements, the number of protons will be told to you by the atomic number. The number of electrons, every proton will attract an electron, so the atomic number will also tell you the number of electrons. And then to figure out neutrons, this is the weight of the atom. This tells you how many particles are in the nucleus. So this is going to, actually this one here is going to tell you protons plus neutrons. Down here, that's what the atomic weight does. So if you subtract these two, if you take 11, the weight of this element, and subtract 5, which is the number of protons, it's basically like you're erasing the protons. Oh, on this one we said there was 5 protons. And you're going to do your own math. 11 minus 5, that's how many neutrons it'll have. You do the same for aluminum. What do the sum of the protons and neutrons in an atom equal? Well, when you add up all of the protons and the neutrons, you get the mass. Usually on the periodic table we call it the atomic mass. Sometimes it's called the atomic weight, but they're both terms that mean the same thing. What do the sum of them equal? Okay, there we got. What are the masses of all the elements relative to? Well, what they do is, for every weight system you have to have a standard, and so they base it on carbon-12. So it's based upon the carbon-12 isotope, which is the most common form of carbon. We'll get to isotopes in a moment. So they basically they figure out, okay, the most common form of carbon, which is really essential to life. They figure out what its mass is, 12 atomic mass units, and that's what they base all the other weights on. So let's see, what are isotopes? Isotopes are that's supposed to be heavy or skinny, if you want to think of it that way, versions of an element. Kind of like me before and after Thanksgiving. Okay, you got the skinny version and then you get the heavier version. Okay, so isotopes are just those elements that have, and usually, how do isotopes of an atom differ? The way they can be heavier is they can add more neutrons or remove some neutrons. You can remove neutrons from an atom. Neutrons have no charge. They can move in and out of the nucleus fairly easy. Why does an atom's mass number not equal its atomic mass? Okay, so two things. Atomic mass. When we look on the periodic table, okay, these are an average number. They're not a specific number. They're an average for millions of these atoms. So let's see, why does an atom's mass number not equal its atomic mass? The atomic mass is an average weight, or mass if you like. I guess it's using mass. Now, an atom's mass number, that is going to be real specific for a particular atom. For example, you can have carbon, what we call carbon-12. That's the most common form of carbon. It has a mass of 12. You can also have carbon-14. We use this for radioactive dating. So what the mass number tells you is specifically what is the mass of a specific element you're looking at. Over here from the periodic table, these are averages. This is the average weight for millions of atoms. If we pull one of those atoms out and we count how many protons plus neutrons it has, that gives us the mass number of this one specific atom. Then if we reach in and pull another one, we may find, hey, this one has, when we add up the protons and the neutrons, this one has a few more neutrons. It has a couple more neutrons in there. If the element is carbon, it will always have 6 protons. You cannot change, an element will not change how many protons it has, because if you give this one another proton, it becomes nitrogen. How is the modern periodic table arranged? It is arranged by increasing atomic number, which means number of protons. Now, what subatomic particle mostly determines an element's chemical properties? All right, so every proton attracts an electron. Okay, that's just kind of how it works on the periodic table, or in nature. And this will tell us, this atomic number tells us how many protons and how many electrons. But with the exception of these elements right here, the noble gases, all of these elements need to either gain more electrons. These guys tend to need to gain more. These guys here tend to need to lose electrons to become stable. So what happens is, what determines an element's chemical properties is going to be the electrons. Now, the electrons are attracted by protons, but when it comes to bonding, chemical bonding is all about electrons. And in the next unit, we're going to talk about electrons that are given away, that are taken. That's called ionic. We're going to talk about ones that are shared. That's covalent. But anyway, it comes down to the physical properties, the chemical properties of an element are determined by its number of electrons, which indirectly is by the protons, but it's the number of electrons that determine the reactivity of an element. Okay, what are the horizontal rows? Okay, they're periods. Vertical columns, okay, they're groups or sometimes called families. Okay, so groups, these are periods. Horizontal means like flat, like the horizon. Vertical means up and down. I always thought the V in vertical reminded me of an arrow pointing down and then up, so up and down. What are the following groups on the periodic table? You know what? You go to page 162 and 163 in your textbook, you're going to have a big giant display spread. The only thing that it won't show you in our textbook, it's not going to color in the halogens. And so the halogens are, let's just scoot over to this side. These are the halogens right here. They're in group 17. So your periodic table, page 163, has these all nicely colored in. We've done that in class, but your textbook left off the halogens. Number 13, which group of elements has only full shells? Okay, it's going to be the noble gases right over here. They have full shells. Okay, so the noble gases. Which group contains inert elements? Okay, it's going to be the same thing. The noble gases. Inert, it means unreactive. So the elements in group 18, they all have their outer shells totally full. 8 electrons, 2 for helium. And then they are also called the inert gases because they do not react. And then the reason they're called noble gases, just like the ancient nobility, they would not interact with the common people. These elements don't interact here with the common elements on the periodic table. Which elements are second period elements? Okay, well, here's the second period right there. You can go ahead and just list the symbols. You don't need to write all the names. Lithium, beryllium, okay? That's it. And which elements are in group 14? Okay, well, group